Hello and welcome everyone to EuroVis 2021 and the third full paper session on multivariate data and dimension reduction. My name is Stefan Bruckner from the University of Bergen and I will be your chair today. We have three very interesting papers lined up for you today. And without further ado, I'll start by introducing the first talk. The first talk is entitled Exploring Multidimensional Data via Subset Embedding. And this is work by Peng Xie, Wenyuan, Xie Li, Wentao, Huang, and Chen and this is joint work by Tianjin University and Fudan University in China. The presentation will be given by Peng Xie, and please go ahead, and we're looking forward to your talk.
Hello everyone, it's a great honor to represent our work on behalf of all co-authors. The title of our work is Exploring Multidimensional Data via Subset Embedding. My name is Peng Xie from Tianjin University in China. We propose a visual analytics approach to exploring subset patterns of multidimensional data. This is a multidimensional dataset example. Each record represents a crime that occurred in Chicago. We would like to explore criminal patterns with the dataset. Existing works use two categories of techniques to explore multidimensional data. The first one is clustering. Analysts use a clustering algorithm to divide original records into several clusters, each corresponding to a data pattern. Subspace analysis, rather than finding record clusters, is to find dimensions where data patterns may exist. A common problem is most existing approaches are finding patterns on the record level. Patterns of multidimensional data, however, are often related to subsets rather than records. A subset is the set of multiple records. For example, the thief subset contains all the thief crimes. The Saturday subset contains all crimes that occur on Saturday. Each subset can have multiple features. A feature describes an aspect of statistical information of all the included records. For example, we can use the count of all included records or the distribution of aggregate values on an attribute as a feature. A subset pattern is a group of subsets having similar feature values. For example, we partition the data into 7 subsets, each corresponding to a day of week. We find 7 subsets form 2 clusters by projecting them, reflecting the crime patterns on weekdays and weekends are different. We can also project these subsets divided on different attributes together. For example, by projecting the crime subsets and the week subsets together, we find the thief subset is close to weekend subsets, indicating thief crimes occur more often on weekends. Discovering subset patterns of multidimensional data is a big challenge. First, there are many ways to partition a dataset into subsets. Second, a subset can have a large number of features. However, subset patterns are often associated with a few subsets and features. The huge search space makes the discovery of subset patterns a challenging and time-consuming process. We propose an embedding-based approach to exploring subset patterns. The core idea is to generate uniformly formatted embeddings for many pre-generated subsets and perform dimensionality reduction and clustering to identify patterns in an efficient way. Subset embedding technique should satisfy 3 requirements. First, the subset embedding technique should handle subsets of arbitrary shapes, which often have different features. Second, the subset embedding technique should capture the similarity of subsets on single features. That is, the subset embedding technique can generate similar embeddings for subsets with only a few similar features. Third, the subset embedding technique should have high training efficiency to enable incorporation into visualization systems. We propose the subset embedding network inspired by multiview learning. We consider each subset a multiview object. Each feature is a snapshot taken by a visual camera from different perspectives around the subset. We will show how this sort can yield a subset embedding network satisfying the 3 requirements. The network structure is on the right. A subset can have multiple features, while subsets selected on different attributes have different features. The subset embedding network consists of multiple subnets, each corresponding to a feature. All the subnets share embeddings of subsets as inputs. The embeddings are randomly initialized and iteratively updated during the training process. Embedding of a subset will only be inputted into the subnet corresponding to its feature, thus enabling to handle subsets with arbitrary features. For example, the embedding of subset 1 will be inputted into subnet 1 and n, and the embedding of subnet I will be inputted into subnet 2 and n. And when two subsets have similar features, their embeddings should be similar to some extent, considering their embeddings will go through the same subnet to reconstruct similar features. This enables the subset embedding network to capture the similarity of subsets on single features. We implement each subnet as a fully connected natural network containing a single hidden layer. The simple structure and few parameters achieve high training efficiency. We develop a visualization system based on the subset embedding network. It integrates three components, that is, exploration manager, subset projector, and pattern explainer. The first component is exploration manager, which implements the progressive data partition that enables analysts to generate various subsets with few operations. Its main body is a tree. At the beginning of the exploration, there is only the root in the tree, which represents the original dataset. We limit it to selecting data on an attribute at a time. For example, we specify week as the selecting attribute to partition the root into 7 subsets and project all the generated subsets. We then select 2 groups of subsets corresponding to the weekday and the weekend, respectively, which form separate child nodes of the root. We further select newly added nodes that contain subsets of weekday and partition it into 24 subsets on hour. Each subset thus represents an hour on weekdays. We also select 2 groups of subsets to form 2 child nodes of the weekday node. Although we limited to selecting data on an attribute, we can obtain subsets covering any attribute value ranges by the progressive data partition. This approach allows us to obtain finer data patterns gradually. The second component is subset projector. It is responsible for creating the projected lattice space in which analysts select subsets that may involve patterns. It integrates rich interactions and automatic methods to assist in selecting subsets. The third component is pattern explainer. It consists of a group of feature cards implemented as classic visualization techniques to show and compare feature values of selected subsets. It uses a consistency measure to quantify the significance of the patterns. We perform 2 categories of tasks to identify the Chicago crime dataset patterns at group and individual levels, respectively. We first partition the data into 7 subsets on week. We project the subsets and find 2 obvious clusters, that is, weekday and weekend. We select them as separate tree nodes and find more crimes occur in daytime on weekdays, while more occur at night on weekends. We further partition weekday subset into 24-hour subsets. We highlight subsets of night which form 3 clusters. We select them as separate tree nodes and find 3 kinds of crimes occur more often at night than in evening, while residents are the main locations. We partition weekday evening on location type and find 5 clusters. We find 2 roadway-related subsets, that is, sidewalk and street, are in 2 clusters. By visualizing their features, we find 2 criminal types and 3 locations are related to sidewalk, while crimes occurring on street are more diverse and even distributed throughout the city. In task 1, we explore data patterns related to subsets of the same shape. We can also explore data patterns related to subsets of different shape. For example, we project the 16 crime type subsets and 7 week subsets sliced from the root respectively. We find weekday subsets and weekend subsets are close to different crime time subsets. The finding indicates that narcotics crimes occur more often on weekdays, while criminal damage occur more often on weekends. We partition weekend on hour and crime type respectively and project all the generated subsets together. We find assault subset is adjacent to afternoon subsets, which indicates assault crimes occur more often in the afternoon on weekends. We partition weekday on hour and crime type respectively and project all the generated subsets together. We find assault subset is adjacent to evening subsets, which indicates assault crimes occurs more often in the evening on weekdays. We use 5 measures to quantitatively assess pattern encoding accuracy and visual perception accuracy of the subset embedding network. The experimental results show that our technique has the highest measure values in most cases. We further visualize projections obtained in the experiment. We can identify more categories in the projections of our technique. This is the instruction video of our visualization system. Thanks for your watching.
Yes, now we are here to answer your questions about this very nice presentation. Please use the Discord chat to post your questions, and I see that there are already several questions. There's an ongoing discussion. So the first question is from Gennady Adrienko, who says this is great work and wonders if your approach can be extended beyond flat tabular data, for instance, to trajectories of moving objects, graphs, or other more complex data types.
Yes, I think my subset embedding network is a general technique. If one thing can be described as some features, I mean the feature is the feature can be any form. Maybe it is a number or a vector. After this, I think the embedding network can generate embedding for this kind of things. It includes the things in the question, maybe a moving object, a graph, or the complex data types.
Thank you. There's another question from Renato Paiola. He says maybe he may have missed it, but how is the exploding space of possible subsets managed? Because given some a large number of elements, there is 2 to the power of n subsets, which quickly may become unmanageable. So he wonders how this is dealt with.
In my case study, user only generates a few subsites, and the number of subsites is smaller than 10. But I think my just like I said before, my technique is general. I think when there is a lot of subsites, or maybe thousands of subsites, my technique can generate embeddings very fast. The result is the experiment result is shown on my paper. If you are curious about this, you can read my paper.
Okay, and we have actually 3 questions from Michael Berisch, who thinks also this is great work. He wonders, can you elaborate a bit on the differences and commonalities to subspace clustering?
I think my work is very different from subspace clustering, because subset patterns is a general patterns. It both related to records and features. So it is a big scope. I think it's a big scope than the subspace clustering.
And also there's a second question about which other patterns other than visual groupings can you interpret, and how can you do that in your projection visualization?
Let me think. In my case study, I find patterns on group level, and I also find patterns on individual level. For example, I find a special kind of crimes that is the nanotic crimes is more related to weekday rather than weekend.
Mm-hmm. And finally, still from Michael, does the user, or what kind of indication does the user get to further dig into a subset? Is there any sort of cue or other hint for the user to dig into a particular subset?
In fact, in our visualization system, we provide two indicators. One indicator is a slicing attribute indicator. Use this indicator, user can find which attribute is more related to data patterns. And another indicator is the metric in the feature card. It describes the significance of the patterns analyzed find.
Let's see. And maybe as a last one, I have another quick question. So I wondered whether you also analyzed the stability of your approach with respect to removing particular subsets, because often there may be subsets that correspond to trivial correlations in a high-dimensional data set that overshadow other things. So how does your embedding change when you remove a particular subset? Does the entire projection change, or is there any sort of robustness in this?
You mean a big data set or high dimensional?
Yeah, potentially both, but specifically when a particular subset is removed, filtered out of the data.
Yeah, I can explain this for you in two aspects. The first aspect is I make a experiment in my paper. In this experiment, there are 2,000 subsites, and each subsite have three and have let me think. Each subsite have 13 features. I think that is what you say, the high dimensional and the big data set. My subset embedding network has performed very well in this experiment. And on the other hand, I believe the visualization system can help user when they explore such a big data set and with a lot of features. Because in my visualization system, I provide some automatic methods such as clustering and some classic visualization technique. That is the feature card, such as line chart, bar chart, and some matrix.
Yeah, so maybe we can explore this also a bit in the chat. But I think there are no further questions from the audience. So thank you again for the very nice presentation and Q&A. Yes, and the second paper in this session is entitled also related to projection guided stable dynamic projections, and this is work by Eduardo Vernier, João, Comba, and Alexandru Telea, and this is joint work between the Federal University of Rio Grande do Sul in Brazil, the University of Groningen, and the University of Utrecht, both in the Netherlands. So please, Eduardo, go ahead with your presentation.
Hello everyone, my name is Eduardo Vernier, and today I'll be talking about how to create stable dynamic projections. That is, when we want to project high-dimensional data that has a temporal component to it. But before we move to the techniques we designed to handle time-dependent data, let's do a quick recap of static multidimensional projections and understand why they are such invaluable tools. Projections take high-dimensional data and create a low-dimensional representation whose visual patterns reflect some notion of the similarity and structure of the original data. High-dimensional data comes in many shapes and forms, but for this demonstration we'll stick with image data, which makes presentation and reasoning a bit easier. We will use the Quick Draw dataset provided by Google, which contains doodle made by people that visited their website and drew many different classes of objects. In our study, we used a subset of 600 drawings from 6 classes, each drawing being a grayscale image with 28 by 28 pixels, which makes it a 784-dimensional dataset, so similar to MNIST. So, what does a suitable lower dimensional representation for this dataset looks like? Here we use principal component analysis, so PCA, to generate this 2D projection, and we can see some patterns, clusters, and some separation driven by the shape and form of each drawing. So for example, rounded shapes, mostly the baseballs are located on the top part of the projection, while the more horizontal drawings are on the bottom left, and the more upright drawings of cellos and carrots are to the right of the projection. With this, we can see some cohesive neighborhoods, locate ambiguous drawings, find similar doodles, and spot different ways to draw the same object. So, why are projections useful? In this case, we are using projections mainly to summarize data and understand relationships for datasets with large numbers of observations and dimensions. So for large volumes of data, like we have here, other high-dimensional visualization techniques such as scatter plot matrices, table views, parallel coordinates, will likely fail to create a reasonable or informative plot due to scalability issues. Also, projections can be used to assist in clustering, classification, prediction, labeling, or as part of machine learning pipelines. It's also important to note that the literature on static projections is very rich, and there's a large variety of techniques available. There are techniques that work with different mechanisms, that reach for different objectives, and have different capabilities or limitations, which may make them useful for one problem or task or dataset, but not for another. And here we can see, other than the PCA projection, which we just saw on the previous slide, projections generated by TSNE and UMAP, which are very popular and capable techniques. For the static case, there are good studies of all these aspects, capabilities, limitations, different styles, etc. And if you want to learn more about static projections, we would refer you to the Spedotto survey, which talks about all these different features in length. But those are static projections, so just the final drawing. But what about dynamic data? So instead of having only the final drawing, what if we could see the steps that the person drawing took to get there? Could we build the projections that help us understand the dynamics of many high-dimensional observations over many time steps? So we want to project a dataset with t time steps because we want to understand its dynamics and evolution over time. The immediate question would be, can't you just compute an independent projection for each time step and then somehow glue them together? Not really, and this is why. This is what happens when you use TSNE to project each individual time step to the dataset and then glue these projections together. There is no temporal coherence between the time steps, and even though for an individual time step the projection is a good representation of the structure and similarities in that particular time step, as a whole, as a dynamic projection, we can make sense of what's going on. There's too much instability, and this animation does not capture the dynamics of the dataset. Now, here on the left we have a stable projection of the same data. Note how the evolution is controlled. As the doodles are being drawn, the positions of the points change smoothly. They start to create clusters, and we can start to tell different patterns apart. We can also judge the velocity of change of the original data. While on the right, all we see are the algorithm's artifacts and stability. So dynamic projections are important because they allow us to understand high-dimensional temporal dynamics, monitor states and events in a multivariable space, recognize recurring patterns, and predict complex behavior. But what is the state of the art in dynamic projections? Here I will mention our EuroVis 2020 paper, in which we compared 9 dynamic projection techniques based off adaptations of popular static methods, such as PCA, UMAP, TSNE, and autoencoders. All of these are being used in our current work, plus 2 more techniques that we implemented for the latest benchmark. We tested these 9 methods on 10 temporal multidimensional datasets, and given that there was no benchmark available of temporal multidimensional data at the time, we built one ourselves, which we also use in the current work. These datasets were extracted from different sources and portray a wide range of temporal phenomena. These are videos, sound recordings, sports statistics, algorithm behavior, and a few synthetic datasets with easily recognizable dynamics. The collection also exhibits significant variation in measurable traits, such as the number of samples, number of time steps, dimensionality, intrinsic dimensionality, and sparsity ratio. We do this analysis to indicate that our benchmark captures an as wide as possible spread of dynamic phenomena, and that the playing field in which these methods will be compared on is fair. Once we run all algorithms on all datasets, we need metrics to test how good these dynamic projections are. These are divided into 2 main types. Spatial metrics, which measure neighborhood preservation and distance preservation. These are well known from the static literature, and they measure how good each individual layout is and how well they capture the structure and similarity of the high-dimensional data. The second type are the temporal stability metrics, which measure the coherence between data change and visual change. Or, in other words, they measure the stability of the projection. Once we compute all metrics for the projections of all datasets, we build a comparative table. So these are the results. This is a very aggregated view. Each cell represents the average metric value for a given technique on all datasets. Dark colors mean bad quality and bright colors mean good quality. And we can see that some techniques perform well for a given metric set. For example, we see that per time frame TSNE and UMAP score highly on neighborhood preservation, especially TSNE, but these per time frame methods don't try at all to preserve any sort of temporal coherence, so their stability is pretty low. While PCA and autoencoder-based methods are very good at distance preservation, and of course the main aspect we're interested in, stability. Overall, there is no clear winner. There's no global method that scores the best for all metrics, but we see that autoencoder-based methods and global PCA are stable and strike a very good balance between all metrics, making them, among these 9 techniques that we tested, the best methods for projecting temporal high-dimensional data. But can we still improve? And we noticed that neighborhood-based methods, such as TSNE and UMAP, they are so popular and well-tested in the static literature through the mechanisms that we use to generate the dynamic projections on this paper, couldn't achieve very good stability. And we wondered if we could design such a mechanism or strategy able to create stable projections while leveraging on their superior neighborhood preservation abilities. But how can we design such a method? Let's start by reviewing the ideas behind the TSNE-based methods we saw on the last table that didn't work very well. Global TSNE and timeframe TSNE are the simplest methods. They are different strategies that use the unmodified TSNE algorithm to create dynamic projections. The difference between them is how data from different time steps is combined to become the input and how the output is divided or combined to create the different time steps of the projection. But in essence, they are based off the vanilla TSNE implementation. While Hauber's dynamic TSNE goes a step further. It adds a new term to the objective function that acts as a brake for points. It basically punishes any movement as a way to encourage overall stability. And this works to a certain extent, but for datasets with complex dynamics, where movement is expected, it tends to fail due to the heavy constraints. Our novel techniques are based off a different idea. Instead of trying to prohibit any sort of movement, we want to guide points through stable trajectories. The goal is to create global influences that consistently and stably steer points, while counteracting the stochastic nature of neighborhood preservation algorithms. And this is how we do it. Our first method is called landmark dynamic TSNE. It draws inspirations from one idea that has been used in the static case and can be utilized to our advantage for dynamic data, which is the use of landmarks. And this is done by selecting a subset of points from the original high-dimensional data, projecting them, and then using these landmarks as guides or anchors to the placement of all points in the projection. This algorithm involves 3 different steps. First, we need a representative set of high-dimensional points. And what we did on our experiments was simply selecting a random subsample of k% points from the full dataset. This is the easiest strategy, but more complex mechanisms can be implemented. For example, depending on the dataset, there might be conventions as to what are typical representatives, or you could use clustering or statistical analysis to get better archetypal observations. The second step is to take this high-dimensional subset of representative points and project it into our low-dimensional space. This is what embeds the landmarks. In our experiments, we use static PCA and TSNE to place these landmarks. Another option, which we demonstrate in the paper, is to manually set the positions of these points. We might want to do this, for example, when monitoring events, or if you want to customize the low-dimensional space into a configuration that may be helpful when performing a specific task. The third part of the algorithm involves figuring out how to make the points that we're trying to project interact both among themselves to create a good layout, but also with the landmarks. So over time, this global influence may steer points through a stable trajectory. And technically, we do this by introducing a second term to the cost function, responsible for making points in the projection be attracted or repulsed by the landmarks, depending on how similar they are in the high-dimensional space. I won't go into too much detail here, but this second term is an asymmetrical version of TSNE, so landmarks influence the points in the projection, but not the other way around, since the landmarks are supposed to act as immovable influences over all time steps. And by modulating a lambda parameter, we can choose how much of this global influence we want, compared to how much of the original local forces from regular TSNE we want. Our second method, which we call principal component dynamic TSNE, also uses the idea of modulating global and local influences to stabilize projections. The global influence part comes from trying to minimize the distance of a point being projected to the position given by the top 2 eigenvectors of the full dataset. So essentially, it makes points want to go to the position given by global PCA, which earlier we saw was stable and had good distance and neighborhood preservation. Its axes are also interpretable, making it easier to understand what the global influence is over all time steps. The local influence comes from regular TSNE attraction and repulsion, so from the interactions of points within the same time step, just like in the previous method and the other TSNE-based methods. And here again, this is implemented simply by adding a new term to the TSNE cost function and trying to minimize it via gradient descent. We see that part of the function is regular TSNE, so the regular attraction and repulsion from points in the same time step, what we call the local influence. And part of it is essentially a pulling force to a position given by the top 2 eigenvector projection matrix. So again, we're trying to use what we know is a stable projection, the one given by global PCA, to guide our points. And just like in the previous method, a lambda parameter modulates the influence between these 2 forces. The next step is to test our new methods, so we build upon our previous benchmark. We ran our 2 techniques on all datasets and computed all the quality metrics. These are the animations from the quick draw dataset, the same from the beginning of the presentation, but all other animations are available online. And the metric results we got were the following. PCD-TSNE, the second method we presented, was very successful. It was as stable as the other state-of-the-art methods, it achieved the best average distance preservation over all methods, and had very good neighborhood preservation compared to the other stable methods, that is, the ones that actually try to preserve temporal cohesion. So if we judge by metric results alone, PCD-TSNE scores better than all compare methods on combined spatial and stability criteria. Our new algorithm also overcomes two limitations of the other state-of-the-art methods. Autoencoders are difficult to set up, optimize the architecture, and take a long time to train, while PCA-based methods are very sensitive to outliers. LD-TSNE did not achieve metric results as good as the other state-of-the-art methods. However, due to how the landmarks work, it is very customizable and can be useful in special use cases where we might want to add meaning or semantics to certain areas of the projected space. Here, for example, we use two different strategies for embedding the landmarks. The dataset we're projecting is called Gaussians. The temporal dynamics are that of high-dimensional clusters collapsing into a single point over time. On the left, we use a simple PCA projection for the landmarks, so all the points adhere to this shape. But on the right, we manually organize the landmarks according to the class label, so we customize the dynamic projection to a specific task. And as points collapse over time, they reach the position of their designated clusters. This is a somewhat simple example, but this capability can be very useful for when we have prior knowledge of the dataset. So, in conclusion, dynamic projections are an important tool to make sense of temporal high-dimensional data. And despite the abundance of temporal datasets in the wild, research on the topic has been minimal compared to the work being done in static projections. So in this work, we propose two dynamic projection methods that leverage on the neighborhood preservation abilities of TSNE. PCD-TSNE uses attraction to the principal components as temporal guides and scores a great balance between stability, neighborhood preservation, and distance preservation, while LD-TSNE uses the concept of landmarks and allows creating stable and customizable projections. Hopefully, we convinced you that our methods work well, and that you should consider using them when faced with temporal multidimensional data. But there is still a lot of margin for improvement, and the goal of our research is not only to create methods that perform well, but to foment developments in the field. That's why we made all our code, dataset, and partial results available online. So just like this paper was built upon our previous benchmark, other researchers may build upon our current work. As far as future work goes, one of our objectives is to extend our methods to handle streaming data. There is already some interesting work on the topic, and even though there's some connection to what we're doing here, because spatial quality and stability are also main concerns, there's an extra challenge when it comes to streaming data. And that is that the incoming data can be anything, and the projection has to learn and adapt to any scenario. While in our work, with dynamic projections, we know from the start what the data looks like from beginning to end. And lastly, additional validation of our methods on more datasets and with concrete use cases and user tasks would be valuable. Hopefully you enjoyed our presentation, and thank you for your attention.
Yes, thank you very much for this nice presentation. And also, I think it's fantastic to see that you're making all your data and code available for the community to build on. And congratulations on that. Yes, let's see. I think we have some questions in the chat already. The first one is from Anna Villanova, who says, she may have missed it, but is there any mechanism to avoid that if a landmark has a high dynamic behavior, that all the related points move with the landmark, which would cause the impression that all points have the dynamics? So maybe you can comment on that.
Yeah, of course. First, thanks for the question. And how we do the selection of the landmark. And this is just the mechanism we implemented. This can be very generic. You can make your own landmark selection mechanisms. There's different things that you can do. But what we did was a very simple strategy, which was take the whole data set, all observations, all time steps, and then from these, select a few observations over different time steps. So we're not just using one observation over the whole evolution of the data set, but we have samples from all time steps. So we have some landmarks that will show the dynamics from in the beginning of the recording of your data, and some on the end. So over the whole dynamic projection, you have representations from the beginning to the end. So that's how we dealt with it, but there are other ways that this can be dealt.
I think that answers the second part of Anna's questions too, whether the landmarks are defined using also temporal aspects.
Yeah, in this case, yes. Mm-hmm.
Yes, we have another question by Kevin Allen. How computational heavy is it to generate comparisons? There may be a first block to adapt to more diverse data structure. That may be a first block. So can you comment on the computational load of comparisons?
Mm-hmm. So our method has basically the same complexity as TSNE. So 10 squares, if I recall correctly. And what we do is just we run it one time for each time step. So if your data set has 10 time steps, maybe you run it 10 times. But we also do some tricks to make it faster, because from one configuration to the next, from one time step to the next, usually there's not a lot of change that needs to be done. So the layout tends to be pretty optimized at this point. There's just a little bit of change that has to happen, and this converges pretty fast. So after the initial steps of setting up the algorithm, conversion happens really fast. So computational load wasn't a big problem for us.
I actually have a question myself. So now also in your experiments, you focused on data where there is an actual real temporal component, but you could in principle drive the temporal component also by another dimension. And did you try this? And do you have any indication of what nature this dimension would have to have for this to make sense?
No, we didn't do any tests like that. We took data from the wild that usually was some sort of measurable measurable experiment, and then it had recordings of, this is one day, those values for these experiments, this is the next day and the other day, and the columns were all the same. So you had like some traits, for example, if you were looking at, I don't know, trial patients, and you had like blood records, all the stats that you might want, those columns are the same. So we didn't use a different column or a different dimension as time. So, but it would be interesting to see what would happen.
I mean, I think with some obvious things, I mean, I think, well, spatial dimensions tend to be of a similar nature as temporal components. So there it could potentially make sense, but maybe there are others too, or maybe there would be tasks where this is also relevant. So I think that's maybe an interesting thing to try out. I see we have another question from the Discord by Farhan Rashid, who says, again, very interesting talk. Have you also checked how, or have you also verified how stable the approach is by choosing different sets of landmarks?
Yes, we did experiments where we had, for example, a set of landmarks that was 100 landmarks, 1,000 landmarks, more or less, and we saw how much that varied on the stability, and has a pretty big impact. Also, which landmarks are those and how representative they are of the data set. That's very important too. So our strategy for our tests was very naive because we just want to see if it worked. So just like the random selection, but then you can build more robust mechanisms. So for example, if you use some sort of hierarchical clustering and then you choose a set of landmarks that, or high dimensional observations that you know is very representative, and then you project those and use as landmarks, then you have more of a robust result because your data set will be more representative of what the actual data set looks like. So your landmarks will be more representative of what the actual data set looks like, and you may not just choose some outliers or some very tight knit group of landmarks that might steer your projection a little bit off.
Thank you. Yes, I see there are no further questions at this point. So thanks again, Eduardo, for the very nice talk.
Thank you.
And the final presentation for this session is coming up. The work is entitled Texture Browser, Feature-Based Texture Exploration. This is work authored by Xuejiao Luo, Leonardo Scandolo, and Elmar Eisemann from the TU Delft. And Xuejiao is going to give the presentation. Please go ahead.
I'm Xuejiao Luo. The title of my presentation is Texture Browser, Feature-Based Texture Exploration. In this work, we aim to facilitate exploration of large texture image collections. Texture is a key characteristic in the definition of the physical appearance of an object. It's a crucial element in various computer graphic applications. Nevertheless, they are often abstract and hard to describe with natural language. There are huge texture image collections, both natural and computer-generated. Here is an example from a very large texture database called Describable Texture Dataset, the DTD database. Each of these images belongs to one category according to their attributes. We saw examples of such metadata for the first row. In each category, there are of course many more textures. The question is how to distribute them in an intuitive way so that navigation or retrieval can be easy for humans. A lot of work focuses on image retrieval, but most is not geared specifically towards textures. Metadata-based image retrieval systems have been successfully applied in most web-based image search engines. This fits general images well since keywords often work well for objects. But for texture, syntactic description of texture characteristic is not straightforward. And even creating appropriate metadata is a very difficult task. For example, default texture images. In addition, large amount of manual effort is needed in creating images, descriptions, or attributes. An interpretation of such information can vary among individuals. Color-based retrieval methods compute the color histogram to guide the search task, but are not focused on the actual content of the texture. Nevertheless, in our context, the structure of the images plays a much larger role, and color can even be adapted in a post-process. Content-based image retrieval relies on combination of colors, textures, local geometry, or any other information that represents and can be extracted from images. In this situation, it's common to rely on example images when searching, which are not always available, and these systems do not lend themselves well to a fine-grained search. There are good examples in image retrieval with deep network, but they require specific inputs, like query images or keywords. and they don't target navigation or exploration. However, they usually rely on level data, which is time-consuming and costly to create. This limits their generalization to large collections or different databases. Our solution is inspired by these approaches, as we leverage the powerful semantic feature extraction capabilities of neural networks in combination with model visual data analysis. Visual exploration of embedded datasets using t-SNE is used extensively in the medical field. Although the focus of t-SNE is the exploration of relations between data points, it doesn't translate well to textual database exploration and retrieval tasks, which is addressed in our solution. Now let's go to our solution, automatic semantic embedding. Here is an example of our special embedding for the DDD database. Our system automatically groups images which have similar characteristics in 2D space, and the position of these images generally reflect their textual features in a semantic manifold. This is done using only the image contents, without using any metadata. Okay, how do we achieve this? Well, we rely on a well-known image classification network to create semantically meaningful high-dimensional feature vectors, which we then embed in 2D space using t-SNE. Since modern image classification networks have a large capacity and are trained with large databases, their layers are able to encode the texture of high diversity. And there are also evidence that this common image classification network, like VGG16, mainly rely on identifying texture rather than shape. Therefore, VGG16 descriptors are very specialized for distinguishing textures, and so we measure the similarity of images by the distance between their activations of VGG. Since the activations of later layers represent more complex and semantically meaningful features, we use the penultimate dense layer of the VGG16 for computing this similarity. Although these layer activations can represent features very well, their dimensionality is in the thousands, obviously too high to be displayed to human eyes in a direct way. Furthermore, some dimension may be redundant, especially for a texture image. For human interaction, we need to provide a low-dimensional visualization which makes understanding and interaction easier. This motivates a manifold mapping. So we use t-SNE to embed them the high-dimensional features into a 2D space, as shown here, to facilitate exploration. In addition to this, our system integrates several targeted tools. We build upon some known techniques and also introduces novel solutions to control the embedding. In this section, I'd like to introduce these tools and interface. While the embedding can successfully group similar textures, it fails to give a good overview due to too much information being displayed at once, especially with texture collections. That motivates us for providing a clustering mechanism to its navigation, and to allow the user to identify categories in the embedding, so they can then focus on clusters of their interests with the desired property. We achieve multi-scale clustering using mean shift. Users can decide which scale they prefer, and we provide a landmark for each cluster that shows examples of images in the cluster. User can access into a cluster so other clusters are not present anymore. This helps with the focus and eases navigation. The texture may manifest different features at different scales. For example, in this image below, At fine scale, the texture looks like a grid or wicker, but at a coarse scale, it looks like diagonal stripes. As such, some users may look for this texture in clusters of wicker textures, or others may look for it among stripe textures. So where do we place it? Well, why should we constrain the image to be present in only one position in the search space? We identify textures that display different characteristics at different scales, and place them in two locations, based on their fine scale and large scale features. To achieve this, we pre-process images by multi-scale Gaussian blurring. We obtain feature vector for both the original and blurred versions. If the features are sufficiently different, they will be embedded at different locations in the 2D mapping. We can see how some images move in position with different scale features. In general, around 10% of images in the DDD database displayed different low-scale and large-scale characteristics, and are therefore replicated in the embedding. To give a more concrete example, this shows two images and their embedding neighbors based on the feature vector of the original and blurred versions. In the first row, we can find the texture in two positions. In the original fine scale, it appears in the group of dots, and with the embedding of the coarse or lower resolution version of this same image, it appears in the water group. For the image in the second row, in the original resolution, we can locate the image from the group with similar fine texture of textile, and in the vicinity of its lower resolution version, they are similar in larger scale features. While the Disney embedding already leads to naturally grouping texture in a semantic way, we would like to offer the possibility for a user to emphasize certain groups of texture or features, or to express a children image neighborhood. The goal is to use more space in the embedding for images similar to a children image. Similarly, textures that the user can mark as less relevant should use less space. This should be done in a continuous manner to avoid generating artificial clusters. To achieve this, we propose the prioritized Disney embedding and allow users to set customized attention width. Practically in the interface, if the users want to focus more on some specific group of textures, they can pick some textures and add width to these images. Then the distribution is updated by our proposed prioritized Disney. Then the region with larger width is emphasized, and the region with small width is shrinked. This shows the method for achieving such effects. Disney models similarities among data points as distances, and minimize the callback level divergence between the joint probability of the low-dimensional and the high-dimensional distances. We put here the equation for modeling the distances of the low-dimensional distribution. With the prioritized Disney, according to user assigned attention width for specific texture in the interface, we compute width for all samples based on the distances in the initial Disney embedding. The width varies in a continuous manner relative to the distance of user-selected textures. Afterwards, the widths are in turn used to weight the distance of the low-dimensional model, and the embedding is recomputed or updated with this width in effect. We also offer an image-based search tool. In practice, users often already have something in mind, or even an example cinema image of what they want to find. We want to allow users to sketch or provide their own image to guide the exploration process. The image shows where the user can use this feature. Users can choose to draw a simple sketch or import an existing image. After obtaining such a guiding image, there are two steps to obtain the corresponding landmark images. Firstly, the VGG latent vector of the guiding image is extracted as the same procedures in the initial embedding. The extracted VGG vector of the sketch image is then matched to the most similar texture from the database by the score difference of VGG vectors. Here are some examples of matched sketch-to-texture images. In some cases, a user may find a pattern they like, but knowing the color they will like. Since not all color and texture combination exists in texture databases, we provide a simple tool to recolor textures. Therefore, we provide the user with a simple recoloring tool to give further flexibility when choosing an image from the database. This tool clusters the texture colors and allows users to modify clusters individually. It works similarly to the technique published by Chen. We conducted a user evaluation to validate the effectiveness and advantage of our system. In the first part of our study, we compare against displaying images on a grid using thumbnails, which is the standard file system solution. It also requires no metadata, as is the same case for our system. In total, 16 users participating in the evaluation. They had no prior experience with our interface, but were computer science students. Results show that the average time to retrieve the target texture with the grid view is substantially reduced by using our interface, with a more than threefold improvement, even when applied by an inexperienced user. User experience is also improved. We noticed that overall, users prefer the overview mode slightly more than using the clustering feature. Further results show that the clustering approach works better for some textures when they correspond to a well-defined and identifiable group, for example stripes, but not so good for textures without an immediately recognizable large-scale feature pattern. To test keyword use for texture selection, we provided users 2 out of the 47 labels from DDD database, porous and interlaced. We asked users to retrieve one texture representative of each word, with no time limits, which we saw here. The red frames highlight the retrieved image that matched the keyword as a description label in the DDD database. For the first keyword, porous, only half of the participants found a texture that carried the corresponding label in DDD. But all textures exhibit porous features. For the second keyword, interlaced, only one of the retrieved texture was labeled as such in the database, although all textures show interlaced patterns. This highlights the difficulty of texture retrieval via labels, as user interpretation of a keyword can vary greatly. In contrast, a texture retrieval system navigating in a semantic way, such as our presented system, provides a more intuitive and general way of approaching such tasks. We also evaluated features of the interface, image-based search tool, and prioritized listening. Since these two features aim at aiding retrieval in large and cloudy databases, the texture database used here contains more than 5,800 texture images. 16 users were randomly divided into 2 groups, each with 8 users. For one group, users were asked to complete a retrieval task with only the overview panel of our interface, and without using the prioritized listening, an image-based search or other functionality. For another group, users were required to use such features. Results of that with the prioritized t-SNE test. The average time of retrieval was reduced by roughly half. With the image-based search tool, the improvement is even higher, with a roughly 4 times reduction in retrieval time. To conclude, in this paper, we presented a system that facilitates the task of exploration and retrieval in large unlabeled texture collections. We organize images based on semantic features, and additionally provide several tools to improve the exploration of image groups that share similar features. One of these tools, our proposed prioritized t-SNE algorithm, can enhance the visualization of areas of interest for a user, and might even find applications beyond the scenario of this work. The result of our user study saw that our proposed system is a considerable upgrade to traditional file system and grid-based interfaces when exploring texture images. Thanks for listening.
Yes, thank you very much for this very nice presentation. And we have time for some questions from the Discord, so I encourage you to post your questions. Maybe we can start off with one of my own. So you primarily motivated this by applications in 3D art, but did you consider and maybe already started to explore other types of application? One thing that comes to mind immediately when talking about texture, at least to me, is, for instance, histology data, where texture can have a significant impact when judging, for instance, the malignancy of a tumor. Did you consider trying to employ your approach in this context?
Does you mean that just apply my approach on the other database, like general image, not only the texture images?
Well, specifically, I think histology data is often heavily characterized by texture features, and it seems like a very good match for the capabilities of your technique. But yeah, at least it's something to definitely keep in mind. I think, because in particular, I think also the multi-scale aspects of your approach could be very nicely suited to this type of medical application. Do we have any other questions from the audience? Looks like we do not yet have another question at this moment. Oh, I'm wrong. I see there is one. How well would this scale with an even larger database? Would there be simply more clusters or rather larger ones?
Actually, VGG16 was trained with millions of images, and the DDD database was now used. Contains like 5,000 database. We also did a test of our approach on this whole database, and it also works well. So the size of the database is no a problem with our approach.
But how in terms of performance, but also is there any change with respect to the patterns or clusters that you are presenting when you have a very large database? Or did you look into the robustness with respect to data size?
Actually, we did test on two different database with different size, and it also works well. The only difference is the time for the t-SNE algorithm, but this is offline and it's just one time for running. And after that, all the interaction are in real time. So I guess it is only affects the time of running the t-SNE.
I see.
Yeah.
I think there are at this point no further questions in the Discord, but of course you are encouraged to continue the discussion and later on, and I think you will be available for further questions. So thank you again for the very nice presentation.
Yeah.
Yes, and we are at the end of what I believe was a very interesting session. Of course, as just mentioned, the discussion should not end here. Please use the Discord or also the Topia chat to continue interacting with the authors. From my side, I want to thank all the speakers again, and of course, I want to thank you for your active participation. And that's it, and enjoy the rest of the conference.